Okay, this is Lecture 9, and we're going to talk about network simulation in this lecture. Essentially, we're going to talk about the conservation laws and the equations governing network simulation. So we're going to set the background for what we have to understand, or what we have as governing principles that are going to allow us to solve these network problems. And we're going to specifically use the HardyCross method, which is developed in the 30s and it's fairly old, but it's a nice hand solution that you can do, and it demonstrates the concepts. There are other automated programs which use numerical methods that are much more sophisticated than HardyCross to solve it efficiently, but this gives a nice way to look at how to solve these problems. I'd like you to look at the notes that I have scanned and placed on Blackboard from Chin's book on his explanation of the pipe network simulation. And then I will point you toward example 12.6.1 in Maze is an excellent example of how to work the HardyCross method. I'll be working some problems in class as I get a chance. This is what we're talking about in terms of a pipe network. This is a situation where you have flow coming in here, and you have external flow at this location, external flow at this location, and external flow at this location. And then you have these various interconnected networks of pipes and various loops. And so the key is, how do we solve the problem where we have flow coming in, flow going out externally, and then we want to know what is the flow in each one of these individual pipes. You can see that they're interconnected, and it takes some iteration scheme or scheme that we put together here in order to solve for this, and the HardyCross is going to be the method we're going to look at. So it's important, and why do we even care, is because we want to be able to look at, make sure that we meet the minimum design flows and design pressures in each location in our network, and that we don't have anything undersized in terms of the flow of connections, or the pressures would drop there below minimum standards. In order to solve these problems, we're going to look at the conservation laws, and essentially we're going to note that the conservation at each junction node, if we look at this network here, this intersection of these four pipes here at node 10, that's called a node. This would be a loop going here from pipe 15 to 11, 17, and 2. That's a loop. So within this particular pipe network, I've got I got 1, 2, 3, 4, 5, 6, 7, 8 different loops in this pipe network. So at each one of those junction nodes, I'm going to say that the sum of the flows coming into that junction network minus anything going out of it, external. So when we look at this Qij, we're talking about in the pipe, the various pipes that are coming into the node. And so flow can either be coming into the node from a pipe and going out of a node from a pipe. That would be still in the Qij. The F is essentially the external flows that go out of the system. They're totally lost to the system as a whole. Now you'll note that in Maze he uses Q external. So the nomenclature I'm following here is essentially what we have in Chin, whereas in Maze he talks about the sum of the flow coming into the node, in this case node I, would be these pipes here. In this diagram we're showing this coming in and these two going out in terms of the internal flows. So you'd have one pipe having a Q in and two pipes having a Q out, and then the external flow is Q external, and that's this side over here on the right, the sum of the external flows. And so again, noting that Chin uses F to note the external flows and Maze uses Q external. In terms of the nomenclature here, NPJ is the number of pipes meeting at node J. Qij is the internal flow rate in a pipe I into node J. Inflows are positive, outflows are negative. To follow the nomenclature of Chin, we continue with the FJ being an external flow, being outflow is positive, being the external flow out into away from the pipe system. And then NJ is equal to the number of junction nodes. So this I here is a junction node, the little circle right here. All right, so the conservation law is continuing. So there was, at each node, we've got the sum of the flows, and the inflow and outflow have to be equal to the external flow. And if we have no external flow in that particular node, that means anything coming in has got to be equal to that going out. The other conservation law is that we have the sum of the energy losses plus the energy gains, which would be basically by a pump, around a loop must be 0. So if we take this loop here as B, C, F, and E, and we blow it up out here, if I take the energy loss in pipe BC plus the energy loss in CF plus the energy loss in EF plus the energy loss in BE, that has to equal 0. Now, that means that we've got to choose a direction, because if the flow is going, and I'll cover this in another slide in a second, as the flow is going, if the flow is going from B to C, that's clockwise, and then C to F, that's clockwise. But you might also have, if you'll notice over here in the real network, you might actually have flow going from BE-EF, and they're flowing out here at this external flow at node F. And so we're going to have a scheme where in the positive or clockwise, the clockwise direction is considered to be a positive energy loss, and counterclockwise would be a negative energy loss. And we will sum those energy losses, keeping track of the direction, being whether they're plus or minus. And around a loop, we're going to have the conservation law, which tells us the sum of those losses minus the pump input. So there's no pump in this particular situation, so we have no HP. But if we did, we would have to subtract that off. That has to equal to 0. And this NL is the number of loops. So in this particular example, we've got 1, 2 loops. And then we've got NPI is the number of pumps, or number of pipes in loop I. That should be an I. That somehow this is, the PowerPoint has capitalized these I. So that's not loop 1, loop 1, that's loop I. And so essentially we could look at this and say, okay, in this loop I here, you've got 1, 2, 3, 4 pipes. This loop I plus 1, or loop 2, would be 1, 2, 3, 4. Notice they share a common pipe here at BE, and we'll talk more about that in a second. So if I look at trying to solve the pipe network flows, I'm going to use these two conservation laws that I talked about. One is at the node, which says that the sum of the flows into the node has got to be equal to the sum of flows out of the node. Those are from the internal pipes minus the external flow FJ. And then around the loop, I've got, which I just explained, the sum of the energy losses around the loop minus the energy inputs by the pump have got to equal 0. If I combine those two conservation laws with a head loss equation, and I've presented here both the Darcy-Weisbach, I mentioned the Darcy-Weisbach and Hayes and Williams, and we'll show it on subsequent slides, but we're going to concentrate on Darcy-Weisbach, as you well know. And I've got a pump head curve yields a mathematical description of the flow problem. So the head loss equation, Darcy-Weisbach here on the left, and then if I've got any pumps, I can represent that by a pump head curve. HP is equal to A plus BQ squared. Now you've seen that. That's the form of a pump capacity curve. So essentially, what we're talking about here with this N, this Q to the N power, this K is going to be based on the type of energy head loss equation we use, and the N will be as well. For Darcy-Weisbach, this N is going to be 2. For Hazen and Williams, it's going to be 1.85. The K value is going to have different forms depending on whether it's Darcy-Weisbach or Hayes and Williams. And so if you look at that, we've got Hayes and Williams, that K is basically, if you remember that the Darcy-Weisbach equation says HL is equal to F L over D V squared over 2G, I'm going to rearrange that and assume that, or not assume, but with the knowledge that V is equal to Q over A, and A in a circular pipe is pi D squared over 4, I can rearrange that to get this K value of 8FL over pi squared G D to the 5th power. And there's all what the various constants stand for, those variables stand for. For the Hazen and Williams equation, as I mentioned, the Q is equal to 1.85 in that, and rearranging the Hazen-Williams head loss equation, I can get my K is equal to this, and my phi value is going to be different whether I'm using English or SI units. Now, if I'm solving for the pipe networks, I'm going to look at that continuity relation. And if I look at that, I can say that if I approximate the value of the Q in each pipe as QJ, I know that when I make that first approximation, that's not right. But the true value is going to be, the approximation is QJ hat, which is this one here. The true value, QJ, is going to be whatever that approximation is plus the error in the approximation. Okay? So you have to follow along here. I know that I look like I'm going down various rabbit trails, but you have to bear with me here, and we'll see where this comes out at the end, I'm hoping. That you'll be able to be clear, especially if you listen to the lecture a couple times. If I plug this equation here into my head loss equation, I can see that instead of Q, which is the true value, I have this Q hat plus delta Q, which is the approximation for Q plus the error of the approximation delta Q. And so I've got that as the head loss is equal to K, and then this value to the nth power. And again, for Hazen and Williams, it's going to be 1.85. For Darcy-Weisbach, it's going to be 2. If I take the binomial theorem, which basically you can look that up in a mathematics textbook or a calculus textbook, but I can expand this equation here when I've got an additive or a summation in parens to a certain power. I can use the binomial theorem and say that that's approximated by K times Q hat n plus n Q hat n minus 1 times delta Q plus n times n minus 1 over 2 Q hat n minus 2, so on and so forth. And if I'm assuming that my first approximation is relatively small, which even if it's large relative to what we think of the errors, let's say by several CFS, if we were measuring in flow in English units, cubic feet per second, even if I'm an error by 2 or 3 or 4 CFS, that's still a pretty small delta Q in terms of error when I look at this binomial equation. And later on you'll see that it kind of comes out in the wash because I'm going to go through iterative loops to minimize the error and get the correct answer. And so I'm going to assume that delta Q is small, so I can get rid of these higher order terms, which is these that are squared and so on. And so I end up simplifying it and saying that the head loss is equal to K Q hat n plus n Q hat n minus 1 times delta Q. Now, if I'm looking at this and I've said that is my value for the head loss, I can then further expand that out and multiply through by K, which again the K is that is a coefficient based on whatever the energy loss equation is. Now don't get that confused with the minor loss terms, okay? So you have to keep things straight here. This large value or large capital K in this context is the terms that are in that friction loss equation. So this is the head loss in the direction of flow. Basically, if I expand this term, and as I've mentioned to you earlier, we've got to look at these head losses in each pipe. And we're going to have to assign a positive value for one direction and a negative value for the negative direction, or for the other direction. And so I'm going to assume in my loops that clockwise is positive and counterclockwise is negative. Excuse me. Now, as I look at this and I place this expanded value of the head loss equation I can say, in order to keep the signs correct, because we have to know whether we've got positive or negative flow, I can say that positive flow is in the clockwise direction, and negative flow will be in the counterclockwise direction, and the signs on the head loss are preserved if I expand and say, okay, Q hat to the n is simply Q hat times the absolute value of Q hat n minus 1, which will always make this term take on the sign of whatever the direction of the flow is. And then on this side over here, I just say that the Q hat is always the absolute value of. That way I'm using this first term to set whether the head loss is positive or negative depending on which direction I'm going. All right, and then I'm going to utilize the conservation law where I've summed the head losses around the loop, and which I've written out to you. This is Chin's equation 296 is right here. If I plug this value in for this is what it looks like. I'm basically summing these head loss terms around here, and I'm at this point just ignoring the pumps. Okay, and so this is for I, which is for loop I, and then if I had a second loop, it'd be loop I plus 1 or 2, 3, all the way through the number of loops. And so we've got this is going to be a major equation that we're going to reorient here in a second to get our correction factor. So the scheme is going to be, you're going to look at the pipe network, you're going to assign through conservation of mass or continuity in each node, you're going to guess at what the flows are in each pipe. And then you're going to take this equation here in a second in rearranged form, and we're going to solve for the head losses and come up with an estimate of the error correction. All right, so, and that error correction is taking this equation right here and then rearranging it to where we solve for this error delta Q I. And so what I've done is, you can see I've just taken this equation right here and assuming that around here, in order for this error to be corrective all around the loop, we have to make the assumption that the error in every pipe is the same. So we've made the same error. Now we know that's not correct, but we're going to go through multiple iterations and we're going to see that it will come out where that error continues to minimize every time we iterate to get a closer and closer estimate to the real value. So this delta Qi, which is going to be our error estimate, is estimated by minus the sum of everything around that loop. All the K is for the individual pipe pipe J in loop I, and then the assumed value of Q times the absolute value of the assumed value Q times n minus 1. And again, if this is Darcy-Weisbach, which we're going to use, this is going to be n minus 1 is 2 minus 1, or just to the first power. Same thing down here. I'm going to sum those around times n, which is the number of, which is 2 in this case, because that's our value for the Darcy-Weisbach equation. So this is going to be the basis for the HardyCross method. And so now we need to talk a little bit about the scheme for the HardyCross method, because right now you're looking at these equations and you're still going, even though I've tried to explain it, you're still going, what the world is this all about? I'm not really sure I know what's going on. Well, that's why I've said you're going to have to listen to the lecture maybe once or twice and then see, look at this method and see it worked when I work an example in class. And I may even put one on tape lecture where you can kind of see the methodology. So the first thing you're going to do in the HardyCross method is you're going to compute the Kij values for each pipe. Now remember that I is the loop and J is the individual pipe, and so each pipe is going to have a value of K. And again, this K, and I've put it right here where you can easily see it, is based on the Darcy-Weisbach equation, is the 8FL over pi squared G in the diameter of the pipe to the 5th power. And so if most of the time I'm going to give you a value, or on all these problems I'm going to give you a value of F. If you don't have it, you're going to have to make an assumption of F and then check your assumption, but that's very labor intensive. And for this purpose, something I would give you on a quiz or an exam, you're not going to have time to go through it's bad enough going through the iterations to solve and get rid of the errors in the queue. If I had to, I'd double your work or triple your work if I had to also then go through and assume various values of F and check your assumption. All right, so once you get all the K's computed for each pipe, then you're going to assume a reasonable distribution of flows in the pipe network, ensuring that continuity is satisfied at each junction node. And so if you look at that, you're going to look back. Let me pull up a network here. So in this situation, I've got 10 CFS coming in here, and a reasonable assumption might be to assume 5 CFS going this way, 5 CFS going that way, because I know that I've got 10 coming in, I got to have 10 going out, and then I've got 5 coming in here. I will have to have 5 going this way, and then as I come into this node here, I've got 5 going here. I'm paying attention now, and I know that I've got to have 4 going out down here, 2's going out here, 4 going out here. So I'm going to have to play with this and make assumptions in BC, BE, EF, and CF that would make sure everything at every node I've got continuity preserved in my first estimate. Okay, so let's go back to our cookbook here of the method. So that's part 2, and then part 3. Then for each loop, I'm going to compute the values of K, Q hat times the absolute value of Q hat n minus 1, noting that in the if I've got flow going in the clockwise direction, that's going to be a positive Q hat. If it's in the counterclockwise direction, it's going to be a negative Q hat. And I'm also going to calculate the K values times 2, in this case for Darcy-Weisbach, times the value of the assumed Q to the first power for Darcy-Weisbach here, because n is equal to 2 for each pipe in the loop. And then I'm going to calculate the delta Q. Again, the delta Q is going to be calculated by summing in each loop all these values of K, Q hat times the absolute value of Q hat divided by K, the sum of all the K times 2 times Q hat to the first power, and then that's the negative value. And that's for each loop. So I'm going to have to repeat that exercise for 2 loops here. So I've got the first loop, I'm going to calculate a delta Q for it. I'm going to then apply my corrections, and then I'm going to the next loop here, calculate delta Q's for it, and apply the corrections. And that'll become evident in the example problem. All right, so I'm going to add the correction with the correct sign to the estimated flow of each pipe, as I just said. And then I'm going to repeat steps 3 and 4 until this value of delta Q that I compute each time are reasonably small. And what that means by reasonably small, if I report my values to 3 significant figures, and let's say that I'm going to, for cubic feet per second, I'm reporting it to 0.01 CFS. So I would report things like 2.01 cubic feet per second. That means my delta Q needs to be equal to or less than 0.01. All right, because that's where my significant digit is, my last one. I don't need to go out to the thousands, so I don't need to go out to 0.005. As long as I get it to 0.01 or less, I'm done. All right. Now, I'll work an example on the board. I've also developed a spreadsheet that's in Blackboard, and you can see it there to how it's done. I've asked you to note, I've already answered it here. If I don't give you an F value, which I will, but if I didn't, you'd have to make an assumption and then check your assumption once you calculated the Q values. All right, that's the lecture for Lecture 9. And so now you need to proceed and attempt to work the problems, see how they're worked in the book. As I've mentioned, the example in the book, 12.6.1, is a good example for you to look at.